So I'll leave that manic reaction up and maybe we'll get to it. How long do we get? We got a while.
You're probably going to run out of space. And you're probably going to erase it anyway.
Probably. Maybe I'll start writing small. Although I want to make it big enough that more people can actually see it. So there's a reaction of beta-ketoesters. So if we were to make this, one question I'm going to ask you is, what would we make that from? What would the starting material for making this be, and where could we have gotten that? If instead of doing a mild acid workup, we actually do a strong acid workup, and heat it, we can get a decarboxylation, and the product will actually be yes. So I'm going to ask you two questions. One, where did that come from? Retrosynthesis. What would we use as a precursor to make that? And two, what the hell is going on here? That's obviously not reversible because when CO2 gas is gone, it's gone. And I'm just going to erase this because you're right. I'm going to run out of time. Run out of space. Right up there again. No way I'm not running out of space. So if you were asked, provide the mechanism for this reaction and fill in the question mark, which would you do first?
Wait, is that a trick question?
No, because you have to do both.
Which would you do first? Is there a wrong answer?
Well, let's say this was the quiz on Tuesday, and he was like, shit, I have to get some points. Where are the easiest points to get?
Well, I would do the retrosynthesis.
When you do a problem like this, right, the first thing you have to do is accept that you got a zero. It's like, I don't know how to do this, it's a zero. And then you start clawing for partial credit points. And well, I got it, maybe I can get one partial credit point. And then if you get that, it's like, well, maybe I can get a second partial credit point. I read an interview with a Marine from Vietnam one time, and they were like, they had kept alive and gotten through past enemy lines for a really long time, and they were asking what the secret was, and the guy said, well, every morning you wake up and say, I'm going to die today. And once you've decided you're going to die today, you have complete freedom of movement. You can try anything because you've already given up and assumed you're going to die. And so every day you wake up and say, well, today I'm definitely going to die. And it never happened. Like I said, they were able to take risks that they normally wouldn't have taken. So just accept, it's a zero, right? Zero. So now what do we do?
That is not how I think.
I mean, one option is it's a zero and then you just turn it into all.
I said I would do the retrosynthesis first.
You would do the retrosynthesis first? Okay, do it.
You can do kind of what we did with the ketone. Like, we're doing what we just did.
We are. We've got to disconnect a bond. And the bond that we have to disconnect is that one.
Oh, shoot, really?
We have to mentally add the alcohol back across that bond, right? Because we're forming a new bond, we're making a beta-ketoester from a ketone and an ester.
Wait.
Right, so we're going to have to disconnect
I don't think that's the right one.
that bond. Which one did you want to disconnect? I want to disconnect this one. Which one do you want to disconnect?
Well, you're making me feel like I'm very
No,
wrong.
go ahead. I mean, there was often more than one possible way.
Oh, well, like, because wouldn't you have an aldehyde if you disconnected where you're disconnecting?
No, and I'll explain why in a second. But which bond do you want to disconnect? Because it might be an alternative route to the same thing.
Oh, well, I was going to do the one, like, where, like, keeping the ring as one thing and then separating, yeah, right there.
You want to do that one.
Uh-huh.
So let's disconnect that bond. What would the starting material have to look like? There's usually more than one possibility. Often one of those possibilities is a better possibility, but there's often more than one possibility.
Because then you would have the ketone.
So you would start with the cyclohexanone,
Yeah.
and then you would be using dimethyl carbonate, right? Not unreasonable. This carbonyl group is a little bit more
because it has to
stabilized than
leave.
other carbonyl groups because this carbonyl group has two methoxides. But if you were to make this enolate, you could certainly attack that and you could kick out one of these. So that's
And it
not
has
an
to-
unreasonable disconnect.
And it has to be like with the oxygen on both sides of the carbon because one of those groups has to leave.
Right.
Okay.
You have to kick out an alkoxide in step 3. Right? Step 3 is that
Right.
loss of leaving group.
Yeah.
If this were not another methoxide, if this were like an alkyl group,
Then it would just be like a
the
diketone.
product would be a beta diketone, not a beta ketoacid.
Right. Okay.
So your product, if you react with these two, they actually look like this. That reaction would go. Right? That would be a good reaction. Right? You'd be using the ketone and an ester. You'd be using the ketone as the donor, the ester as the acceptor, but that wouldn't be the product we want. To get the product we want, we have to use that metal part. Right? So that's not unreasonable. What if we disconnect this one?
Oh, so it would be the ester.
Then we have
There,
the ester
right.
here. And we have the ester there. And it would look like that. And if I redrew that, it would look like this. Right, 7 carbons. We have methyl ester on both ends. And we'd be forming a new bond between our donor atom here, atom 2, and our acceptor atom.
So is this one the better option because it's an intramolecular one, so it would go faster?
So I like this one for 2 reasons. One, it's an intramolecular reaction, and the intramolecular reaction is likely to be faster because of kinetics. And the other, this is completely symmetrical. So I don't have to worry about 2 different products. Carbon 7 and carbon 2 are identical, or 6 and 2 are identical. So either way, I'm going to take off the same hydrogen, and there's only one possible way. So that's nice. And this could have come from this.
Right.
If I start with cycloheptene, treat cycloheptene with ozone, dichloromethane, followed by hydrogen peroxide, I will get dicarboxylic acid. 1,7-heptane dioic acid. I can then do a Fisher acidification on this with methanol and catalytic H2SO4 to make the dimethyl ester. And treating that, sodium methoxide and methanol. 1, followed by aqueous acid workup, with ammonium chloride. Water is going to generate beta-ketoacids. So in 3 reactions, right, 1 to leave it to make the diacid, 1 to convert the acid to the diester, and then the Claisen condensation, in this case Diekmann condensation, I can get that product. There's nothing wrong with disconnecting this bond and using dimethyl carbonate and cyclohexanone, except that it's an intermolecular reaction, so it'll be a little slower, and the carbonate is less readily attacked than the regular ester because that carbonyl group is more stable. But that kind of reaction could work.
Perhaps this was a quiz question. You probably wouldn't want it to be the bond I broke, though, because you really can't.
Well, then you'd have to start with cyclohexanone, but you can make cyclohexanone very readily. You can make cyclohexanone from cyclohexane if you wanted to. Br2, H new, bromide, heat up with water, make the alcohol, ECC.
Well, I meant
ketone.
the other one.
Right. No worries. Oh, the dimethyl carbonate, just buy that.
Oh.
You can have dimethyl carbonate. That's just the dimethyl ester of carbonic acid. So there would have been nothing wrong with that. It's just that this is probably a neater, cleaner approach.
Gotcha.
There's often more than one answer. But usually when there's more than one answer, there's a better answer. And usually, often anyway, the better answer is the one that separates the molecule into 2 more similar sized fragments. But in this case, it was the intramolecular versus intermolecular that was the deciding factor. So we got some points. We get a 0. But there's a bunch of points associated with the mechanism as well. And then we're going to heat this up. Sulfuric acid and water. Of course, the hydrogen ion is what we really have. Crank that up to 150 degrees. Boil the shit out of it. So, what would you do? Let me rephrase that. What did you do when you were confronted with this exact same question on page 9 of the recently done exam?
I would protonate the oxygen, the ester.
We're gonna hydrolyze the ester, right? This is a reverse Fischer esterification. And it's exactly the same reaction that you did to hydrolyze the ester to make the carboxylic acid on the exam. At least I hope you did. That's what you should have done. And I always assume you're going to do what you should do. Right, so protonate, nucleophilic attack, 2 proton transfer reactions to get the proton on methanol so we can have water leave. The intermediate is a tetrahedral intermediate. You don't really have to write this out, right? Because see this mechanism a few hundred times. started with beta-ketoester. And now after 6 steps, the reverse of the Fischer esterification, we have beta-ketoacid. You might be asking yourself the question, why did I draw it like that? Instead of not drawing it like this. There's beta-ketoacid. Why did I draw it like that? The answer is I drew it like that to emphasize the fact that there's a 6-membered ring here where that hydrogen and that oxygen are right next to each other in a 6-membered ring. It's a very favorable reaction to deprotonate that, kick out CO2, and form methyl. That's a 6-membered ring. Transition state, which means it's aromatic. It's quite favorable. And we liberate CO2 gas. And carbon likes it when it can become CO2 gas. So you can't make this stuff. If you have heat, beta-ketoacids are unstable. If you actually want to isolate the beta-ketoacids, you better be really careful. And when you work up this Fischer esterification, you want the acid to be pretty dilute, and you want to not be heated. Right? So if you've got a slightly more concentrated acid and you heat it, this 6-membered ring transition state to blow out CO2 and form methyl is going to happen. And then you can do a tautomerization. Generate the product. Like this, right? 2-step keto-enol tautomerization. So these last 2 steps here are so it's actually 9 steps to get all the way from the beta-ketoester to the ketone. 6 steps is the reverse of the Fischer esterification. Then you've got your T blowing out CO2, and then 2 steps to take that enol form and tautomerize it to ketone.
Can you explain what's happening with the ketoacid? Again, why that's breaking apart?
So it's a 6-membered ring transition state, which means it's aromatic, which means it's very stable. If this pi bond plucks that hydrogen off, this O8 bond can break and form the second of the 2 pi bonds to become CO2, and then break this bond here to form the phenol.
Okay.
So it's 6 electrons flowing in a ring, and we've seen a bunch of examples where 6 electrons flowing in a ring provides a nice stable transition state, which makes it a favorable reaction. So that decarboxylation of beta-ketoacids, it's also the case for beta-diacids. Beta-diacids are just as unstable as beta-ketoacids because they can undergo the same kind of 6-membered ring transition state. It's that that makes these 2 syntheses useful. So we have 2 syntheses that exploit that. The acetoacetic ester synthesis, which has as a starting material either ethyl or methyl acetoacetate, start with acetoacetic and the malonic ester synthesis. Which has as its starting material a dimethyl ester, for example, of malonic acid. And it's interchangeable whether you use methyl or methyl. This is dimethyl malonate. Because it's the methyl ester of propane-dioic acid. Which no one will ever refer to as 1,3-propane-dioic acid. They will always refer to it by its common name of malonic acid. So 1,3-propane-dioic acid is malonic acid. The dimethyl or diethyl ester of malonic acid can be used as the starting material, and it's cheap and you can buy it. Both of these are cheap. Acetoacetic. Readily available, dimethyl malonate readily available, and you can use those to make carboxylic acids. In the case of the malonic ester synthesis, and you can use it to make methyl ketones. In the case of the acetoacetic ester synthesis. So this part comes from malonic ester synthesis. Look that wrong. Case of the malonic ester synthesis, or the acetoacetic ester synthesis, this piece comes from the acetoacetate. In the case of the malonic ester, this piece comes. So basically, you're looking at making a new bond from the alpha position. So 3 carbons in the case of the acetoacetate will come from the starting material. 2 carbons in the case of the malonic will come from the starting material. And you can make any kind of substituted methyl ketone you want, and you can make any substituted carboxylic acid you want. pKa here, remember, is around 13. pKa here, remember, is around 11. So in both cases, we have a very acidic hydrogen that's sandwiched between 2 carbonyl groups. So we can take that off pretty readily. So we can form the enolate. And now we can form a new carbon-carbon bond by reacting that with an alkyl halide. So in this case, if I react with 1-bromo-2-methylpropane, I can get a nice SN2 reaction on that enolate. put my R group in. And this is my group that I was trying to add. Right there. And now hydrolyzing that ester. Sulfuric acid and water and heat. Generates beta-ketoacid. And that beta-ketoacid will undergo the same decarboxylation reaction that we saw before. To generate phenolate. Which, when it undergoes decarboxylation, will form phenol. Here, right, that came from the acetoacetic, but just came from the propane. And if I wanted to, I could have actually put a second substituent on there. This could also be replaced. So we could actually have two different groups attached to that alpha hydrogen rather than just one. It'll be sterically a little bit less favorable because once you deprotonate this to form the enolate, there's more steric hindrance. But you can take both of those hydrogens in the acetoacid acetate off in succession and generate two different ones. So anytime you see a methyl ketone as your product, the acetoacetic ester synthesis is a possible way that you've gotten to that methyl ketone. And anytime you see a carboxylic acid as your product, the malonic ester synthesis starting with dimethylmalonate is a way that you can get there. Again, right, we can take that hydrogen off by using the oxide ion. It doesn't matter which direction we go now, because this is going to form the enolate. And then that enolate can be alkylated. What I want to alkylate with to make the product that we had is a benzyl chloride or benzyl bromide. And this is a particularly good SN2 reaction because the benzylic position is more reactive. So if you're going to introduce a benzyl group, you usually want to do it last because this SN2 reaction is faster than a regular SN2 group. So I wanted to introduce one alkyl group and then the benzyl group as well. I think the benzyl group second. So now I've made that new bond. I've got my benzyl group in place. If I heat that up, I will actually cleave both of these esters. I'm not going to show that mechanism. There's 12 steps, right? 6 steps to cleave the one ester, then 6 steps to cleave the other ester. And you make a beta-diacid. That 1,3-dioic acid or beta-diacid is unstable. It decomposes covered fragment here came from the malonic ester. And this fragment here came from methyl chloride. So dimethylmalonate by enolate alkylation, right? You make the ester enolate, alkylate it, hydrolyze the ester, and then it spontaneously decomposes to give off CO2. That'll generate the substituted carboxylic acid. Right, in this case, 3-phenylpropanoic acid. Phenyl group on there. And this is a route to alpha amino acids that are not one of the 20 common alpha amino acids. The 20 common alpha amino acids are best made by chopping off steak and hydrolyzing all the peptides in and isolating the amino acids from the protein. But if you want to make an uncommon one, starting with carboxylic acid like this, right? We know that the Helfel-Orcholensky reaction, we treat this with bromine and PBr3, we can put in an alpha bromo group. And we know that if we then treat that with ammonia as a nucleophile, displace that bromine and I've showed it with an NH2 group and an OH there, but it will actually initially be an NH3 plus and O minus. Right? And this is now an alpha amino acid. This one's phenylalanine. So if you wanted to make large quantities of phenylalanine in the lab, the malonic ester synthesis to make this carboxylic acid, followed by Helfel-Orcholensky, followed by treatment with ammonia, would be a way to get that alpha amino acid. And you can put anything you want here, right? I put that benzyl group there, which is the R group in the phenylalanine. But if I wanted something here that's not common, if I wanted some kind of substitution on my benzene ring to use as an enzymatic probe or something, I can make any alpha amino acid I want from the carboxylic acids that are available through the malonic ester synthesis. So that was a lot. 2 minutes before, so we're almost over. Claisen and Diekmann, right? Very much analogous to the alkyl condensation. The acetoacetic ester synthesis and the malonic ester synthesis are both based on this decarboxylation reaction and the instability of beta-ketoacids and beta-diacids because of the 6-member ring transition state. So synthesis of methyl ketones in the case of the acetoacetic ester synthesis or carboxylic acids in the case of the malonic ester synthesis. And those are good reactions. So there's going to be a quiz on Tuesday. The mechanism for either Claisen or Diekmann will probably be on it. And then maybe there'll be a little synthesis problem. There are separate videos for Claisen, for Diekmann, for acetoacetic ester, and for malonic ester synthesis, and pre-recorded videos as well. So if you want to see them again with a different example, I think I have different examples. You can look at those. So I'll tell you about the manic reaction on Tuesday if there's time. I think there'll be time. And then we're also going to talk about alpha dicarbonyls as opposed to beta dicarbonyls. Claisen and Diekmann make beta dicarbonyl compounds, beta ketones, or beta ketoesters. What if you wanted to make alpha diketones? And that's section 23.4, which is the last section. We just talked about sections 1, 2, and 3 in chapter 24. Are there questions?